Hello again, this is Mark Summers from Summers Technical Services. So we're continuing on with our homework assignment working on tensile test data, creating stress strain curve, and now we're going to use Excel to use the data that I gave you for the class assignment and create an Excel spreadsheet where we're going to extract this data that we learned about in the last video. So I've created a spreadsheet here that has the data that I gave you. So it starts out with no load, and it's got a gauge length of 2 inches, which converts to 50.8 millimeters. And you're going to type in your data. So rather than let you watch me type in my data, for student 0, this is my data for the load. And as the load increases, the length of that gauge length continues to increase because the thing is stretching out. So your numbers will be different, but similar. So the first thing we need to do is convert newtons into pounds, because the problem statement says I want all the answers to be in PSI. So we got to change newtons into pounds and length into inches. And so we can do that with a conversion factor. Just go to the Googles and look up a conversion factor, and all I'm doing is taking D7, which is this cell right here, and then dividing by the conversion factor, and I'm doing that for all the values here. So now these newtons are now turned into pounds here. And I'm going to do a similar thing with the length. I'm going to take, in this case, it's taking E7 and dividing by the conversion factor. And so you'll do that. And all I'm doing is selecting this first cell, rolling it down, and doing a Control D to roll that down. And so now this is E8 divided by 25.4 and E11 divided by 25. So it increments those cells down by 1. And so now I've got my data that I gave you on the homework problem. I've now converted it to pounds and inches. So now we need to do a stress strain plot. So I want to put the strain in the first column because that's on the x-axis, and then y on the second column, which is stress. Now I need to come up with equations to do that. And so the strain is the change in length divided by the original length. So I can write an equation for that equals change in length is going to be that cell, I'll put this in parentheses, equal to that cell minus the original length, which is minus this one, close parentheses, divided by the original length, which is that one again. So take a look at that. That's E8 minus E7. That's the change in length going from here to here. And you divide by the original length, which is E7 here. Now, if I roll this down, I don't want this E7 to increment because I always want to calculate the change in length as the value at this load minus the original length, which is all the way back at the top. And so I want to put a $sign in front of that 7 and a $sign in front of this 7. And that just tells Excel, if you roll me down, don't increment anything with a $sign in front of it. And so I'm going to select this one, roll that down, Control D. And now I am keeping E7. And so this one, for instance, is the change in length at this load, which is this number minus this number, that quantity divided by the original value, which is always this guy. So now I've got the strain for the different load conditions, and now the stress is going to be force over area. Well, I got my force right here. The area I need to compute, and the area is going to be equal to what? Pi divided by 4 times the diameter squared. And so that's the area for all these stresses. And so I'm going to use that over and over again to calculate stress. Pi over 4 d squared. So here, this is going to be equal to the load, the force, divided by this area. So at that point, The stress is that force divided by this area. And I want to do another $sign in front of this 13 because I don't want to increment this down. I want to increment the load down. So I'll put a $sign in front of 13. I'll roll this down, Control D. There's my stresses. There's my strains. So now it's time to do my plot. And so I can grab this data and I can go to Insert somewhere. Insert, and I want to do a scatter plot. I'm going to do a scatter plot with lines and some points indicating where the data points are. You can choose whichever one you want. And there's my curve. That's my stress strain curve for my material. And I can change these axes and I can put I want a minor increment so I can see. I want to do my 0.2% offset rule. And so maybe I'll tweak the axes, and why didn't that work? Format, add minor grid lines. There we go. So now I can see what's going on better. So first thing I can do is drag this thing down here. First thing I want to do is find the ultimate strength. Well, that's easy. I want to say the ultimate strength is the maximum value of this column right here. So boom, there's my ultimate strength. And now maybe I'll calculate the Young's modulus. So I want the slope of this line. It goes through 0, 0 here. So this point here looks like a good one. That's about 35,000. And so that's 1, 2, 3, 4. That's the 5th data point. And so maybe I'll calculate Young's modulus. It's going to be equal to stress at this point right here. 1, 2, 3, 4, 5 divided by the strain at that value. Right? I could have picked this point or this point or this point, but 1, 2, 3, 4, 5. That 5th data point seems to be pretty high on the curve. 1, 2, 3, 4, 5. Might have picked the 6th one, but it looks like it's starting to peel off from where it's a straight line portion of the curve. So I could have used any of these points here. So it looks like I used that one. And that gives me Young's modulus, stress divided by strain. Now the yield point. Well, now I need to get in here and zoom in over here. And I need to do my 0.2% offset rule. So I can find 10, 8, 6, 4, 2. So that point right there, I need to draw from 0.002 strain. I need to draw a line very carefully parallel to that line. And wherever it crosses the real data curve, I can walk over here and I can pick off what the yield point is. And you should be able to get it easily within 1,000 psi. But you got to draw a nice straight line. You can't be doing wiggly lines. And so get a straight edge out, get a sharp pencil out, draw that line like we learned in the last video, and pick off your yield point. And then that will give you all the answers we're looking for, right? The only other thing we might be able to do is ask what is the percent elongation, and we just find the strain at failure, which is right here. Strain at failure is 0.165. So percent elongation is going to be strain at failure times 100. So move the decimal place over 2 decimal places. The percent elongation will be 16.5%. And that would obviously be a ductile material. And I've got, this is a slightly modified curve here, but I did this automatically. There's my 0.2% offset line. I calculate what the Young's modulus, yield strength, and ultimate strength is based on the exercise we just went through. So your numbers will be different, but the same exercise. You'll do the same exercise. So that should get us through homework 3. The first 2 problems you should be able to figure out pretty quickly. We'll review this all in class next time. And until then, have a good one, and we'll see you in the next video.